That would be the same with any of the connections, any electrical connections between the two machines.
Obviously, you've got to have connections between the service module and the command module.
And fuel, you have to have lines in there for the fuel, everything else, and all the controls.
All the electricity that's generated in the service module, fed into the command module. Command module doesn't have hydrogen fuel cells. It doesn't need them. It has batteries. It has batteries.
Well, the antennas are on that stage as well, right?
Yep, they are. So now they got another problem. I mean, this is ridiculous. If Apollo was supposedly the real thing, which it wasn't, but if it was supposed to be the real thing and everybody believes it was the real thing, and they're now just copying what they did with Apollo, and they're finding it's failing in relatively benign conditions, the only conclusion that any sensible person will reach is that Apollo was fake, because they haven't solved these problems yet. It's a sad commentary on the ridiculous performance that they showed us all with Apollo. They were so proud of it. It was so monumentally achievable, a monumental achievement. The whole thing was huge. And now they're finding that they can't duplicate it. Well, come on, guys. That means you didn't do it the first time. That means Apollo was fake. We've been saying this for years.
That's the interesting thing about the human condition.
Yes.
You look at people that are considered brilliant or geniuses or whatever, right? And we always look through to basically scientific achievements. But when you look at other people who are brilliant in the medical field, well, take a look at the British Interplanetary Society, imagination to reality. To solve a problem, if you're a medical doctor, you develop the equipment, you design the equipment to be able to do the surgeries better. So we now use orthoscopic surgeries and robotic equipment to help because they're more precise when they're being handled, because the movement of your hand can be reduced down to millimeters kind of thing. So you're much more precise when you're doing very fine surgeries and stuff like that. And that is the imagination of that person putting it into reality. Those people are brilliant people. We only see Neil deGrasse Tyson. Oh, here's space. There's some stars out there, and this is what I think about it. You can't prove it. You can't do anything with those things. So you can't have an opinion about what his idea is. No. You have somebody like Walt Disney, his imagination, he brought it to life. Not only his facilities, in his animation, in everything, the characters he developed throughout. That's the kind of brilliance that we take for granted, but it doesn't give us the ability to deal with the kind of radiation that's in space.
And speaking about radiation in space, I just pulled up this article that Mary Bennett wrote. So she did this article on the bird detector, and that was December 2014. The Orion test flight was flown in preparation for manned explorations to the moon and Mars. Now, she's put out the diagrams and the dose equivalents in millisieverts, and she shows a chart of the radiation exposure. And 10,000 millisieverts is fatal within weeks, and she has it all broken down with the CT scans and the radiation recorded at Fukushima and all the other natural radiation that we're all exposed to each year. She has it all broken down. Basically, in the conclusion of this, it goes back to the same thing. When you look at these charts against what NASA is telling us is there, it makes no sense, because according to this, there's no way they could be walking around on that lunar surface without proper protection from this cosmic radiation.
Yeah, well, this article on the coronal mass ejections that we're looking at, it would take 45,000 X-rays to kill you. That's 45,000 X-rays in a minute. This CME was bursting at 300,000 X-rays per minute, 5 times what it takes to kill you.
Orion, Van Allen belts, and space radiation challenges. The bird detector. Each time one ever mentions radiation, one of the ways they confuse things, one of the first charts in Mary's article, dose equivalent in millisieverts. If you realize it's a logarithmic scale, not an arithmetic scale, it starts to make more sense. And it goes from 0.1 to 1 to 10 to 100 to 1,000. Well, 10 times is considerably more than the graph appears to indicate.
All right, Marcus, let me ask you something. If you look at the graph down here, dose rate in water for the left detector and dose rate in water for the right detector. Well, why are they doing this in water? I don't quite understand that. What does that have to do with it?
It would certainly slow the absorption rate down if you were within water.
The whole thing that you have to realize about those detectors that were aboard Orion is how the test was set up. The detectors are not just running all the time. They take a snapshot once a minute. Okay. And they are in closets inside the machine with sand and water around them. They've got a meter of sand and water around them. All the other detectors on Orion were completely destroyed. But the battery-operated radiation detectors just take a snapshot once a minute.
So it can basically be manipulated quite easily.
This is what Mary said about that. She said, the bird radiation detector report seemingly confirms that the dosimetry radiation data for the manned Apollo lunar flights was collected while remaining in low Earth orbit. Whether deliberately or unwittingly, NASA's own data has blown apart the notion that a manned Apollo crew ever traveled to the moon.
They would not have survived.
Yeah, it's in that table, dosimetry data from US manned space flights. What's confusing is that they're now using milligrays, not millisieverts. So one has to work out whether the two are compatible. So you've got all these different sorts of measurement, sieverts, millisieverts, grays, rads, rems, and they're all slightly different. It's very hard to get a handle on what's real. Mary comes pretty close to doing it.
My understanding of a millisievert is the average absorption rate running around on Earth over a year.
That's fair enough, yeah.
I'm sure if you're not correct, the NASA proponents will make certain that you hear about it.
Well, that'll get 300 comments underneath the video then, because they can all argue about it.
Well, they argue about it forever.
There's no real scale. When you look up millisievert, it doesn't give you an exact scale of what it's doing.
I think Mary's conclusion at the end of her article is very appropriate. This bird radiation detector report seemingly confirms that the dosimetry radiation data for the manned Apollo lunar flights was collected while remaining in low Earth orbit. Whether deliberately or unwittingly, NASA's own data has blown apart the notion that a manned Apollo crew ever traveled to the moon. Thanks, Mary. You're right. And those readings, they go back years, the readings that they put out about the Apollo craft, the amount that they received, is always quoted by people who are trying to deflect from the radiation problems.
Well, if that's the case, then the re-entry data would be completely wrong as well, the speed of re-entry on the heat shields as well. Let's say they got out very close to the Van Allen belts. They were just under the Van Allen belts when they did that 4-hour and 24-minute launch to splashdown. They just shoot it out like a ball and they don't have a guidance system on it. Nothing has to work. It just goes up. It's going to come right back down again, which means if they're close to the Van Allen belts, they're under 1,000 miles out, not the 3,600 miles out that they were going. That means the re-entry speed would be quite a bit less, which means all of that data is just wrong then.
Yeah. Well, if the re-entry speed from low Earth orbit is compared to the re-entry speed from lunar orbit, it's about 50% different. Low Earth orbit speed is 18,000 miles an hour. Lunar return orbit speed is 25,000 miles an hour. So you've got a 50% increase. Double the amount of energy must be dissipated. And obviously the heat shield wasn't up to it, which is why it all fell apart. But it's interesting, that table showing the dosimetry data from US manned space flights, if you look at the reports from Skylab 2, 3, and 4, the daily dose in milligrays ranges from 0.54 to 0.86. If you then look at Apollo 10, it's 0.6. How come they're virtually the same? The daily dose for Apollo 10, which allegedly orbited the moon, is the same as Skylab, which orbited low Earth orbit.
Yeah, it's wild, isn't it?
It makes no sense because beyond the Van Allen belts, the dose of radiation is invariably higher. And the highest one on Apollo is Apollo 14, by the look of it, 1.27 daily dose in milligrays. There's something very wrong here. There's something seriously amiss. You can't have the same dose in low Earth orbit, in Skylab, as you can on Apollo 10. There's no way they would be the same. I'm talking of the daily dose, not the mission dose. And how did they measure the mission dose on Apollo?
Yeah, that's really strange, isn't it? 0.54 milligrays plus or minus 0.3. Now that's Skylab 2. The highest Skylab was Skylab 4 at 0.86. Now that's below the Van Allen belts. Now we're talking about daily dosage here. But now we're looking at Apollo 10 and it's 0.60 milligrays daily dosage. That's hardly any difference whatsoever.
Makes no sense at all.
And that's in lunar orbit. It says right here, lunar orbital flight.
Yeah, same as Apollo 12, daily dose 0.57.
Oh yeah, there's something wrong.
Yeah, because either we are misinterpreting the data completely. I don't think we are. We're just reading the headings. The daily dose in milligrays is the total dose divided by the number of days. It's a simple calculation. Apollo 11, 8.08 days in orbit. Lunar orbit, 1.8 mission dose milligrade. How did they measure that? Where's the information behind that? The daily dose, 0.22. That's virtually the same as Apollo 15.
But it's Skylab. That's the really strange one because Skylab is not that far off from Apollo 10.
No, it isn't. Virtually the same.
And they even give the altitude, 435 kilometers.
Which is what? About 250 miles.
Yeah.
Not very high.
And that's below the radiation belts. Apollo was right out through them, gone. You know, they're saying this is lunar orbit. Yeah. Skylab was below the belts. So why would the radiation levels be the same per daily dosage? That doesn't make sense.
No.
So there's something wrong. I mean, we're not reading this wrong. It says it right here.
Yeah, it does. It's in black and white. There we go.
It is, yeah.
So we're not wrong. We're just looking at the figures and comparing them with what we know about the difference between low Earth orbit and lunar orbit. The two are very different, but the daily dose doesn't appear to change. That makes no sense at all. No logical sense. And if we're supposed to believe it, I'm sorry, NASA, I don't. I don't think you've got the Apollo readings correct. Apollo 9, they didn't go beyond low Earth orbit, and they had very low dosage.
Oh, but I know what they're going to tell you. They're going to say, well, Skylab 3 was up there for 59 days, while Apollo 10 was only there for 8 days. That's where the difference is going to be. That's going to be for the Apollo missions that were around the moon.
No, because we're looking at the daily dose.
Yeah, that's right. This is the daily dose, not the mission dose, the daily dose. You just take the days and you divide how many days it is per mission dose, and then you get the daily dose. That's all they're doing here. But to have 0.60 milligrays for Apollo 10, and then to have Skylab 3.65 and Skylab 0.54, that just makes no sense.
No, it doesn't. It makes no sense at all.
Well, they don't tell you whether they're doing the chart in minutes, hours, days, or whatever. They change that up all the time, and you have to be so careful when you're looking at those numbers. And of course, the original numbers had to be quite nice for Apollo because they just made them up.
Well, the actual duration for each of the Apollo missions comes close to what we're told occurred, like Apollo 11, that's over 8 days. I think we can agree that that was more or less the time they spent from launch to splashdown. They then say that the whole mission dose on Apollo 11, measured in milligrays, was 1.8. So divide 1.8 by 8 and you get 0.22, the daily dose.
Those numbers could be per second.
It could be.
And depending on a CME or any little flare that they weren't measuring at the time, they don't have any data on the CMEs during the time that they were there. They just said that they weren't around at the time. And of course, there'd be lots of small ones, not necessarily pointing at the Earth, but there'd still be lots of small ones because they were fairly active during that time period that they were doing the Apollo missions.
Well, you'd think they would be fairly close, wouldn't you? We assume that the mission dose is the total mission dose of radiation in milligrays.
When they also do them up, they also do just the absorbed, what they calculate as the absorbed radiation into the human body. They never ever give you the numbers outside the craft. That's the ones that you need to know.
Yeah, exactly. Because aluminium craft does not protect against all radiation, certainly not gamma rays.
Oh, they just go straight on through.
Yeah.
This is what Raza was saying with Bart when he did the interview with Bart. They were going over a few of these examples.
This is a NASA chart, this duration. That's where it comes from. So if NASA have got this wrong, they're deliberately misleading the public. That's not their job. They're not supposed to mislead anybody. They're supposed to report the science as they find it, not as they want it to be, but as in reality. And the more they get it wrong, the more they're going to have trouble proving to anybody they can get out of Earth orbit with humans.
Yeah, well, that's why they have multiple files out there with different data.
Different files, different standards.
Yep.
Okay, look at this. This is what is confusing. Take, for example, the Apollo 11 flight daily dose of 0.22 milligrams and dividing by 24 to find out the dose rate of 0.00916 per 60 minutes, which gives a dose rate of 0.038014 milligrams for a period of 249 minutes. Now, this is about twice as much of that registered by the ISS, namely 0.015 milligrams for the 270 minutes of the Orion test. Now, just wait a minute here. This is interesting because taking this time of 270 and doing the same calculation, the Apollo 11 data would only be marginally increased to 0.04 milligrams. These figures are nowhere near the 15.1 milligram registered by Orion, but they are near to the figures registered by the Apollo missions operating in low Earth orbit.
Yeah.
It's very interesting because it says that the Apollo 11 is twice as much as the ISS. That makes sense. But then you go to Apollo 10 and you look at that and compare that to Skylab, and they're the same. Skylab 3, well, you have 0.05 milligrams difference, but that's pretty close. That makes no sense. We're talking about one mission below the Van Allen belts or one mission that's clear outside the Van Allen belts. You're going to have higher radiation outside the belts continually. You're not going to have figures that are bouncing up and down and being exactly the same when you're below the Van Allen belts and you're way out in cislunar space. It's just not going to happen. There's no consistency here. This is what we're trying to make public. There's no consistency here. It's all over the place. It just doesn't work that way. I'm sorry.
The only thing that is consistent is they keep the imagination of space travel alive.
But not the reality.
Well, like I said, you can have all of the talent in the world, but there are limits to that ability. Just because they refuse to do it, it is so easy to trigger one's imagination.
Of course it is.
And it doesn't matter what it is, from a child on. If you look at children, how they learn, how everything else, that search for knowledge or that zest for knowledge, if you like, is there. And then the imagination takes over on top of that.
Yes, and the fact that the Apollo data is out of sync with the ISS and Orion might explain why it is totally ignored by the industry today. That pretty much wraps it up.
And that's why they're never going to get back to the moon, because they never went there in the first place.
That's why they don't consider the data. They consider that all of the architecture of the Apollo missions to be antiquated and outdated. But how can they be outdated if they're the only ones that actually worked? That's like, well, I invented a wheel and it works really well, but it's so old now, we're going to throw them out and we're going to find out how to develop a new method to transport stuff around efficiently. And we're not going to use the wheel anymore. We know it works, but we're not going to use it.
When we were discussing these engines, we were going over the engine that Jeff Bezos had fished out of the Atlantic Ocean. They're claiming that they lost the technology and it's destroyed, or they don't have it anymore, and the schematics are gone and the tapes are lost and you name it. But he managed to get that engine running again. So what's the matter taking one of those engines that are sitting right out there in the museums? They're all made. Everything's there. The pipes, the tube, they're all there. What about the F1 engines that are sitting outside of NASA's other museums?
Yeah.
They're all over the place. Like, these engines are everywhere, and yet they say they can't do them. They won't work anymore, or they can't rebuild them, and they lost this and they lost that. And
Not
yet,
compatible with new technology.
oh, not compatible with new technology. Yes,
Yes,
that's right.
but
Yeah.
it's the new technology that's not compatible with anything because the new technology doesn't work.
Yeah.
So why not just use the stuff that worked? The newest and latest and greatest technology is the stuff that works. So if it's 50 years old, that's the one that works. If we develop a plane that doesn't fly, are we going to get rid of the other ones and say, well, we're not going to use those, they're old? That wing design, that's so old, we're not going to use that wing design anymore. But we can't build one that flies anymore. The old stuff flew, but we're not going to use that because it's not compatible with the new technology.
Yes, and if they really wanted to get to the lunar surface that bad, they would be digging those engines up out of their museums, and they would just be refurbishing, they put new parts on them, and off they go.
Or just back engineer it like they're trying to do with all the UFO stuff.
Oh, yeah, that's right.
I mean, back engineering, it's a standard procedure. You've got something, you want to work out how it was created.
Yeah, just reverse engineer the entire thing.
Remember what this one fellow said? To take a power supply from one of these UFOs, if they have them captured, you take one of those power supplies and you give it to Christopher Columbus. How many years do you think it's going to take him to back engineer that? Just showing how far behind we are. There's no way we could do it. And then Scott said, yeah, well, then give Christopher Columbus a light bulb and ask him to make one. He couldn't do that either, even though they had glass blowing back then. And then I was thinking that, okay, well, if Christopher Columbus or any of his other scientists were to open that UFO power supply up, it's probably going to have some kind of a, nuclear-ish type material in there. So if they open the casing up, it's going to kill them all anyway. And they're not going to know why they died. So it's going to just keep going and going and going, right? It just doesn't make any sense. Really, it doesn't make sense to think that somebody can just open up. Well, like Bob Lazar said, he says one fella died at the base because they had an explosion before he got there, and someone was tinkering with a power supply, and the casing was broken, and it went off like a bomb.
Mind you, the movie industry can reverse engineer that stuff and make it work.
Oh, sure.
Yeah.
Look at the series Fallout. Got cold fusion.
Always 20 years in the future. It's that famous quote from Arthur C. Clarke, isn't it? Any sufficiently advanced technology is akin to magic. We don't have the terms of reference to be able to understand it. Same as giving a light bulb to Christopher Columbus. I mean, give a mobile phone that we understand today, give it to Neil Armstrong in 1969, he wouldn't know what the hell it was. No idea at all.
Give it to Bill Shatner, though.
Oh, Bill Shatner.
Beam me up.
He's been beamed up for years, hasn't he?
Yeah, he's...
Well, at least the flip phones came along, and it looked just like the communicators. And he took credit for that. The prop designers are the ones that should receive the credit for that, not the actors. Well, but because the actors used them, they're the ones that get the credit for it.
There's an interesting reference in this article. It's one of the last references. It's the comment made by one of the deputies at NASA. There's a particular quote which was actually made on BBC television. Dr. Ellen Stofan, Chief Scientist, NASA, and Principal Advisor to the NASA Administrator, fulfills that "don't mention the moon" embargo. Today, then, rather than the cavalier attitude expressed in the US during Apollo, radiation exposure to astronauts both in low Earth orbit and beyond is now a major concern. But note that despite talk of NASA projects concerning near-Earth asteroids and lunar Lagrange point 1, this next statement from Dr. Ellen Stofan, Chief Scientist, NASA, and Principal Advisor to the NASA Administrator, fulfills that "don't mention the moon" embargo. This is the quote. NASA's focus now is on sending humans beyond low Earth orbit to Mars. There are a couple of really big issues. Radiation. Once you get outside the Earth's magnetic field, we're going to be exposing the astronauts to not just radiation coming from the sun, but also to cosmic radiation. That's a higher dose than we think humans right now should really get. If they can't cope right now, they couldn't cope back then, nor would NASA risk any astronauts becoming ill or dying either during or after the missions. And that's a direct quote from Dr. Ellen Stofan, Chief Scientist to NASA and Principal Advisor to the Administrator. And that was made on a BBC Two television interview in November 2014, just before the Orion craft was launched for the first time in December 2014. Dear, oh dear, NASA, sorry guys, you're not really very clever, are you? You always trip yourself up. I like this famous quote right at the end, quote 26. Wernher von Braun comment to Neil Armstrong shortly before his death, quote, by the prognosis of statisticians, you should be dead in space and I should be in jail. At least he was honest, was Wernher von Braun. So we've still got the radiation problem, haven't we? I think Mary's done a very good job on that. Should be read.
Haven't come very far as dealing with it either. The biggest problem with space, I think, is the weight restriction for launches, number one. And that includes fuel, that includes all consumables, even batteries and stuff like that, oxygen, everything else that you have to take with you. But then radiation protection. I mean, you need to start hauling lead up there.
Yeah, you got
Oh, no, you don't need that anymore. Oh, no, you have boron nitride nanotubes now.
Oh, sure they are.
Yeah,
As long as they're 6 feet thick, it might start to work.
Yeah, let's see it all work. I mean, they tell us these things, but they never show it. They never demonstrate it. They just say, we've got the answer. Here it is. Aren't we clever? No, you're not. You're forever trying to fool us. It's very sad. It really is very sad.
Raza and Bart were talking about radiation, and Raza was saying the very reason why the Chinese Space Agency hired him in the first place was to go and research what NASA was using as a radiation shield to protect those astronauts. That was his whole purpose, and to take that information and translate it into Chinese. And the only thing he can come up with is these boron nitride nanotubes. That's the only thing that he says is working so far. But we don't have much information on it. Of course, they're not going to release any graphs or documentation on it that's going to be of any use to us.
So what's wrong with the original spacesuits?
Yeah, good point.
Depending on what article you're reading, 14 layers or up to 21 layers.
Oh, no, it won't fit in with the new tech. You can't have an old Apollo spacesuit in a brand new Artemis spaceship. It won't fit. It won't work. That's what they'll try to tell you.
Especially when an X-ray goes straight on through them. Doesn't matter how many layers they claim they put in or what the layers are for, right? An X-ray, straight through. Like they're X-raying the Artemis suit as well now, showing all the internals of the suit.
So you see the story about the gentleman who visited Neil Armstrong at his home in Ohio. He's a great friend of Neil Armstrong's. And he was talking to Neil about Apollo and various other things. And Neil said, well, I've got a couple of things down in my basement you might like to have a look at. So he went down to the basement, which didn't have much in it, a few cardboard boxes. And one of the cardboard boxes contained his spacesuit. What was it doing in a cardboard box in Neil Armstrong's basement? And
I thought it was on display.
Well, it is now.
But it's been there forever.
You sure?
One of the first things they did, the museums had it on display since the early 70s.
Ah, but do we know it was the spacesuit he used on Apollo? We don't know for certain.
Well, none of them are suits. They're just practice suits.
Exactly.
If that person was visiting him in his home years later and he had a spacesuit there, what is the official one with so-called the moon dust on it that's on display? Because that's been on display since at least 1972 or 3.
You might well ask. Maybe it was the practice suit they've got on display. Maybe the one in the basement, which was just tucked away in a cardboard box as if Neil Armstrong had very little interest in it, was the real one. I don't know.
If you had gone anywhere, you're not going to have much interest in it.
That's the same as they're coming up when the astronauts are dying and they're coming up with all kinds of artifacts and stuff and cameras and you name it that they so-called have stored away, right?
Which again, it all confirms a lot of what we've been looking at. That Neil Armstrong basically was an honourable man, but it was not in his interest to start talking about faking it. He wasn't going to do that. It would be so upsetting to his fellow astronauts if he was seen to be diverting from the path of truth. So he didn't. He just never talked about it.
That is one of the most unusual things, that you would have an entire group of people that accomplished something as incredible as what they accomplished, and then not have any interest in working for that company anymore or being associated with them in any way, shape, or form. And of course, that includes all of the astronauts who were no longer working for NASA at the end of it. Why would that be?